Welcome everyone and happy hydraulic jump day. April 16th. It's a very auspicious day. You know, it's actually considered really good luck if it's raining on a hydraulic jump day, and it was pouring earlier. It's kind of like how you want a white Christmas, right? You definitely want a rainy hydraulic jump day, so that means it's going to be a good one. I'm going to begin with the poem about hydraulic jumps. All right? Let us all observe the hydraulic jump. Seeing its majesty, in my throat is a lump. Supercritical upstream and subcritical down, the sequent depths never give me a frown. I will always remember rapidly varying flow and appreciate the jump's spectacular show. So, helps us get in the spirit of it. All right. So, we are going to go back in the lab later, but before we do, we're going to talk about underflow gates today. Just a couple of reminders. The homework 11 is due right now, and then a week from today, you'll have homework 12 due, which gets into chapter 14. So, any announcements, questions? Yeah, that was my poem. Yeah, thank you. All right, so what we're talking about today is gates, and here's a picture of a pretty simple rectangular gate that would be used in an irrigation system. And you can see the way that the gate is raised and lowered is just as simple as a rebar handle that's been welded onto the plate. And so this is just something as simple as a metal plate. And the bigger gates get, the more sophisticated they have to be in terms of reinforcement and also the hardware to raise and lower them. Because as the gate gets bigger, it needs to be a thicker piece of metal and it's much heavier. And so you can't just lift and lower it by hand, particularly when there's water pressing on the gate. Because as water pushes on the gate, it creates friction against lifting it that's going to be added to the weight of the gate itself. One place that gates are used pretty extensively is in wastewater treatment plants, and here in Huntington they have a series of gates pretty similar to this really simple one here that they open and close to try and distribute the flow among the different basins that are treating the wastewater. They're trying to equalize how much gets into each of the chambers, and they just use gates to do that. Here is a pretty sophisticated gate that is, as you can see, it has a curved shape to it, and the purpose for this is to make it easier to raise and lower, to try and avoid the case where you've got a lot of pressure acting against the frame that makes it more difficult to raise and lower. And so by having a curved gate like this, the advantage is that all you have to do is raise the weight of the gate through, which is acting through a radius, and the pressure of the water acting on it doesn't increase the amount of force required to lift and lower it. So here is the discharge equation. It's just a matter of adding the specific energy at 1 and equating that to the specific energy at 2. And so the energy at 1 is going to be the depth and the velocity head. Here you can see that we're writing the velocity head in terms of flow rate Q. And the reason why we do that is sometimes we're going to be solving for an unknown depth, either upstream or downstream. Usually an unknown depth at 1, because as we'll have an example a little bit later, we're going to try and find out how much the water pools behind a gate. So what is the depth Y1 when you close the gate a certain amount? Because most of the gate openings are rectangular, we can simplify the expression to the flow per unit width, lowercase q, as is shown there. And there is energy loss as water goes through the gate, and one way that that energy loss is observable is with the contraction, that the water depth continues to get lower downstream before it gradually will begin increasing again. And here you can see that coefficient of contraction times the gate height is where you get the gate opening Y sub g. These wigs are hot. Anybody else feel like it's really a good insulator? On a cold day, this would be a good hat to wear if it's like snowing outside. All right. So this equation is valid if there was no energy loss. We know that there is energy loss, and so in a bit I'll show you how to account for the coefficient of contraction and what's the actual flow rate through the gate when you do account for it. But here's a cross-sectional view just showing that radial gate, and I think you probably will get a sense for why the benefit of having a radial shape is the hydrostatic force is always going to be pointing towards the axis that it's rotating about, and so that's not going to add any additional hydrostatic force to the difficulty of raising it. Whereas in contrast here, this gate is being pushed against a frame. And so when you lift the gate, you're lifting not only the weight of the gate, but also the effect of the friction pushing against the frame for the gate on the left. So we apply the orifice equation. And last time I said the difference between the real orifice equation as a jet going into the air and the case here is that the water is in contact with the channel at the bottom. So that's one aspect of energy loss. And the other is just that as the water is approaching that opening, there's turbulence that has to be accounted for. And so we wrap that up into the coefficient of discharge, C sub D. And there are a couple of different ways to estimate what the coefficient of discharge is. And one of them is by taking into account both the coefficient of contraction and then the difference in depths upstream and downstream of the gate. And so here's an approach that we'll use in an example here in a minute to try and estimate what flow rate can make it through a rectangular gate. So here's that example. Gates are not always as wide as the channel that they're in. And this example kind of lets you know about that. It says that there is a gate that has a width of 1.5 meters and a channel that has a width of 4.3. So here is the channel width, and at the end of that channel is a gate that is only 1.5 meters wide. So here's the gate, and this is a top view obviously that we're looking at. And so what I'd like you to do is go through the steps of trying to determine what is the flow rate through the gate when we know the gate itself, W, is the height that it's open. So 45 centimeters is the gate opening height. Then Y2, the contracted depth is 27.5 centimeters. And so with those two measurements, you can calculate the coefficient of contraction. Once you have the coefficient of contraction, you can calculate the coefficient of discharge, C sub D. And then from there, you can calculate the flow rate. The B that it's mentioning here, just as a warning, usually we use B to mean the channel width. But here, it's referring to the width of the gate. So it only depends on how wide the gate opening is, not how wide the channel is. So go through the steps of calculating Q, starting with first C sub C, then C sub D. All right. Different books use different notations for the height of the gate opening. Here in the diagram, it's labeled as W. In the equation here where it says Y sub G, that just means the depth of the water going under the gate. So here I've said Y sub G equals W. So the first thing we do is calculate the coefficient of contraction, and it's right in the ballpark of about 0.6, as most coefficients of contraction are. When we go in the lab in a few minutes, we'll see, you can actually visually see that contraction where the downstream depth, what's shown here is Y2. I've got it set up right now so the downstream depth is about 0.9. And so the gate itself is against a ruler. So if you get a chance, take a look and see what is the gate height opening versus what is the actual depth of the water downstream, and you'll be able to see the coefficient of contraction in action there. Coefficient of discharge, you put it into the formula, get that's 0.5822. So ultimately, when you put in all of the variables, the flow rate through that gate is going to be 2.86 cubic meters per second. Now, there's a linear relationship between the width of the gate and the flow rate through it. So if we needed to get twice as much flow through this gate, all we'd have to do is make it twice as wide. And we have room for that in the channel because the channel itself is 4.3 meters wide, but the gate is only 1.5 of it. So that would give some flexibility in the capacity through the gate if it was needed. Okay, today when we play around with the elevation of the flume, we're going to drown the jump and then make the jump run away from the gate. So we'll see both of those conditions that were talked about in class last time, where we were trying to find the location of the hydraulic jump. But let's say we want to have the ideal case. And the ideal case is that the jump sets up right downstream of the gate with no additional running necessary. So to have that ideal case and prevent the jump from drowning, the first step is to calculate the normal depth based on the stream characteristics. So you'd use Manning's equation and the slope of the channel, the roughness of the material, the channel geometry, and find out what's the normal depth, meaning under steady conditions. And you assign that normal depth to y2, meaning you're going to have a hydraulic jump, and we want to have it so that the downstream depth of the hydraulic jump, that downstream sequent depth, is the normal depth. So here the water's flowing supercritical, it jumps up to subcritical. What we want to have the ideal case is we want the normal depth to be this downstream depth, y2, after the hydraulic jump has occurred. Okay? Now, we want to find out if the slope is subcritical, and so we compare the normal depth to the critical depth. And we can calculate the critical depth, y sub c. If it's a rectangular channel, it's pretty easy. It's the flow per unit width squared divided by g to the 1/3 power. So the reason for calculating the critical depth is just to find out, is the channel, is it subcritical? And sometimes the phraseology that is used is, can the channel support a hydraulic jump? And the channel that's supercritical can't support a hydraulic jump. And so we need to find out, basically, is yn greater than yc? That's what we're looking for. Because if this is true, if yn is greater than yc, that means that you've got conditions where a hydraulic jump can arise. Now, what will be causing for us the hydraulic jump is that there is a gate. And so the water is pooling upstream of that gate. Now, if we close the gate, that means the depth is going to get shallower on the upstream end of the hydraulic jump, and so that gives us a deeper downstream jump depth. But if we open the gate up a little bit more and open it more, that will cause the jump to get closer to the gate. And so what we need to calculate is what's the maximum gate opening that's going to prevent the hydraulic jump from bumping into the gate and drowning. And so you can set it equal to the upstream sequent depth divided by the coefficient of contraction. And we'll do that in an example. It'll be the sequent of the normal depth. And so remember, a momentum depth diagram, what's that showing you is for a certain momentum function, and here are the depths where we've got the critical depth, and everything above that is a subcritical flow. Everything below that is supercritical. What we want to do is we want to find out how wide open can the gate be and prevent the jump from drowning. And so the y2, the downstream depth, this would be the normal depth of the channel, y sub n, that we got from Manning's equation. And we're going to want to find out what is the y sub 1 that goes along with that, and then take into account the fact that there is the contraction. So it's contracting a little, then it's going up and jumping. So here we're going to have y1, and here is y sub g, or it was also referred to as with the variable w in the previous slides. So we're going to try and find out what y sub g has it so that after contraction, it's the sequent of the normal depth. So just one more time. We know that ultimately the water downstream is going to flow at the normal depth. It always goes back to the normal depth. So we want to find what's the opposite of the normal depth on the momentum depth diagram. What's the sequent of it? So here's the sequent of the normal depth. And so how big should the gate be opened such that after contraction we have that depth at 1? And here's the equation that we can use, the Bellinger momentum equation for finding the sequent of the normal depth. We're going to set the normal depth that we found in Manning's equation equal to y2 to calculate y1, and once we have y1, we can calculate yg. If you close the gate more than that, the jump goes away from the gate. And if you open it more, then the jump will go towards the gate. So here's the ideal case. What we're saying is, if we open the gate more, the jump is going to go towards the gate. And the reason why is that you basically have to think about the momentum depth diagram. And if you have a bigger y1, then it's going to look for the sequent across the momentum depth diagram. And so if we have deeper than y1, it's going to be looking for the sequent here. And if you go over, the depth is less than the normal depth. And it can't do that, and so it'll drown. So here's the example that kind of illustrates that process that we just went through. We're going to try and calculate for a 5-meter wide canal, and the gate is the entire width of the channel. We have a given coefficient of contraction. Then how much should the gate be open to prevent drowning? Like, what's the maximum you can open up that gate and not have drowning? And then we're also going to try and calculate the depth behind the gate, the depth of the water behind the gate. All right. So we've got a channel like this, and the depth upstream is held back by a gate. It contracts a little bit, then it goes through the jump. And here, after the jump is going to be the normal depth. We want to find the depth y, I'm going to call it before the jump. And then the gate opening height, w. And then we also want to know what's the depth upstream of the gate. Okay, so as is outlined in that step, it says first find the normal depth, and we do that using Manning's equation. Just incidentally, we already know that the width of the channel is 5 meters, the flow rate is 25 cubic meters per second, and the slope of the channel is given as 0.003. The n value is 0.02, and the the coefficient of contraction is 0.6. C sub c is 0.60. All right, so first of all, the normal depth. We're going to use Manning's equation for that. Q is equal to 1 over n, area to the 5/3, wetted perimeter to the 2/3, slope to the 1/2. This is a rectangular channel, so that makes it a little bit easier for us. If we substitute in the numbers that we know, it's 25 cubic meters per second is equal to 1 over n. 5 times the normal depth to the 5/3 power. And the 5 is based on the channel width. 5 plus 2 y sub n to the 2/3 power, and then the slope of 0.003 to the 1/2 power. So we can put that into the solver and find out that the normal depth is going to be 1.78 meters. So here on the drawing, 1.78 meters. Once things get back to uniform flow downstream, eventually it's going to reach that depth. So what we want in the ideal case is we want it to immediately jump up to that normal depth, not have to go through gradual flow in between. So we're going to let this normal depth be the sequent of our, that's going to be the downstream sequent. Okay, step 2 in the process is find the critical depth, because we want to double check that there even will be a hydraulic jump, because if the slope is steep rather than a mild slope, there won't be a hydraulic jump if it supports supercritical flow downstream of the gate. So y sub c is the flow per unit width squared divided by g, and our flow to the 1/3 power. The flow per unit width is 5 meters squared per second. So we want to square that, 9.81 meters per second squared to the 1/3 power. So the critical depth is 1.366 meters. Since y sub n is bigger than yc, yes, there will be a jump. So that means the subcritical slope. So the third part is, how big should the opening be? What's the maximum opening height? Okay, max opening height. We first need to find the depth before the jump using the Bellinger momentum equation. So that's going to be the depth after the jump, 1.78 meters divided by 2. Multiply that by -1 plus the square root of 1 plus 8 times y sub c, which is 1.366 meters divided by 1.78 meters, which is the depth downstream of the jump. That to the 3rd power, and we get 1.022 meters is the jump depth. That's the depth before the jump. So here, the y before is 1.022 meters. And so finally, how big can the gate be opened? Well, what we know is that the coefficient of contraction, the definition of that, is y before divided by the gate height opening. And so what we're really after is finding W. So W is going to be y before the jump divided by the coefficient of contraction. So 1.022 divided by 0.6 tells us we can open up the gate 1.703 meters. And if you open it more than that, then the hydraulic jump will go towards the gate and it'll be drowned. Okay, the last question it asks is, what's the depth behind the gate? So depth behind gate. For that, we just plug it into the equation for the flow rate. We're going to take into account the coefficient of discharge and the width of the gate and solve for y1. Okay? Remember, the way that we calculate the coefficient of discharge is it depends partly on the coefficient of contraction. So I'm going to build that right into the equation. I'm going to have Q is equal to C sub C, the square root of y1 divided by y1 plus y2, B times W, square root of 2G y1. Okay, now plugging in the known values here, we know the flow rate is 25 cubic meters per second. The coefficient of contraction is 0.6. We don't know y1, the upstream depth, so we're going to leave that as a variable. But we do know the depth downstream is 1.066. That is the that's the depth before the jump, after it's already gone through the contraction. Okay? And now the 5 meter wide depth for B, the gate opening of 1.703 meters, And finally, the square root of 2 times 9.81 times y1, which is the upstream depth. So we're trying to find out how much is the water going to pool to be able to get the flow underneath that gate. And when we solve for y1, we get that it is 1.883 meters. So over here, we've just found that here it's 1.883 meters. So it's not that much higher than the normal depth, actually. So we can apply that same process and find out, back in the lab, we could find out how high we expect the water level to get behind the gate. We won't, though, since we're just focusing on hydraulic jumps principally. Okay, any questions about this example or the concepts that it addresses? Yeah. Yeah, I guess that's a little bit counterintuitive to say behind the gate when we usually call it upstream. But I guess the way the logic there is that the gate is holding water back. And so it's the water that's being held back behind the gate. Okay, so what we'll observe, again, just to refresh your memory, is that if we open the gate less, meaning if we have a really small opening, that pushes the hydraulic jump further away. Because you have such a small depth that it has to get bigger before it finds the sequent depth downstream that is the normal depth, y2. If you open it a lot, if you have a big opening, then the gate's moving, the hydraulic jump is moving towards the gate to try and find the sequent, and it ends up drowning before it finds that sequent depth. Okay, the one last thing that we'll talk about is when there's a choke, how you can find out what is what's the specific energy situation that's going on, comparing the specific energy at 1 and the specific energy at 2. So a sluice gate can be used to not just to quantify the flow rate, but actually to regulate it. So it sort of has a dual purpose. And the nice thing about a sluice gate compared to like a broad-crested weir is that a broad-crested weir can trap sediment, but a sluice gate's going to remain clean because it's automatically scouring underneath the obstruction. So you may need to remove floating debris, but sediment, which is usually harder to clean up than floating debris, if you had sediment accumulating, then you have to dredge a channel or, sort of drain it to shovel it out. Now, you don't have critical flow like you do in the case of a broad-crested weir. Remember that when you put a broad-crested weir and it chokes the flow, then there will only be critical flow over the broad-crested weir because the water height upstream pools until it achieves just enough energy to get through the obstruction at critical depth. So just to illustrate the fact that it's not necessarily critical flow when there's pooling with a gate, let's take a look at the situation of what if we have a downstream of the gate, the depth is 0.7 meters, upstream originally before the gate was put in place, it was flowing at 3.5 meters, and so now we want to find out how much is it going to pool upstream of that gate when we have the sluice gate in place like this. So we're going to use the specific energy comparison between 1 and 2 to try and find out the new upstream depth. We won't use the same gate equation that we did on the last example. We're going to take a look at it another way. All right. Okay, so here the flow per unit width, lowercase q, is going to be 36 cubic meters per second. And the channel width is 4 meters. So the flow per unit width is going to be 9 meters squared per second. And we'll use that to find the, actually we'll just use that directly in the energy equation because that's the easiest way for us to do the velocity head. So we're going to first take a look at how much energy is required for flow. So at 2, how much energy is required? Okay, E2 is going to be the depth, Y2 plus the flow per unit width squared divided by 2g y2 squared. This is one of the ways that we can easily calculate the velocity head. Okay, so the specific energy is the depth 0.7 meters plus the velocity head where we've got 9 meters squared per second squared divided by 2g times the depth downstream 0.7 meters squared. Okay, so the total specific energy, E2, is 9.125 meters. That's the energy required for flow. So the question is, at 1, before that gate went into place, is there enough energy or is there going to have to be pooling to have enough energy? So the original energy available before pooling, E1 is going to be Y1 plus flow per unit width squared divided by 2g y1 squared. Okay, so the depth originally was 3.5 meters, and then we have 9 meters per second squared divided by 2 times 9.81 times 3.5 squared. So the original energy that was available is 3.837 meters. And from that we can see that the energy required is greater than the energy available, so there will be pooling. We sort of already, in the example, figured there would be, just the way the drawing is presented. But this verifies that you will have pooling because there isn't enough energy to achieve that downstream depth and the velocity that goes along with it. So what we want to know is how much is the pooling how much pooling will there be? And it's only going to pool as high as is needed to achieve the energy required. So remember that the energy required is 9.125 meters. So it will pool until it reaches that depth, the depth associated with that much energy. So Y1 prime, meaning the new depth after pooling, plus flow per unit width squared, 2g y1 prime squared. So we're going to solve for y1 prime, the new depth. Okay, we know the flow per unit width, y1 prime, plus 9 squared divided by 2 times 9.81 times y1 prime squared. Okay, this turns into an equation that looks like y1 prime cubed minus 9.125 y1 prime squared plus 4.128 is equal to 0. And then we go through that same process as we have before with specific energy equation of finding roots. And the roots of that equation are going to be negative 0.65, 0.7, and 9.075. So the water depth will continue to increase until it gets up to 9 meters in depth. That's how deep the water has to get before there's enough energy to support a depth of 0.9 meters. So today, when we drop the gate into the water, ask yourself, why is the water level rising? And it's rising because you need to have a certain amount of energy to get the flow rate underneath such a small opening. All right, so let's go over the handout that we're going to use for the hydraulic chump day activity.